Nuclear chemistry, continued. Radioactive half-life. So whenever you're looking at radioactivity, one way to quantitate it would be the rate constant that's associated with how fast a radioactive species decays, how fast it produces particles of alpha, beta, gamma, protons, neutrons, etc. And that rate constant, like any rate constant, is abbreviated as the lowercase letter k. So a large K means a fast decay, a small k means a slow decay. And we commonly use a modified version of this constant. So most people are not looking at the rate constant per se. They're interested in a different version of the rate constant we call half-life. And the half-life is the time required for 50% of the radioactive species to decay to something else. In other words, for half of it to be lost and become a new nuclide. And it's considered a very major characteristic of a radioisotope. So a short half-life, and we abbreviate half-life with the symbol T sub 1/2. So a short half-life means a very fast rate and that it's a fast decay. So if it takes a short amount of time for its half-life, that means it only takes a short amount of time for half of it to be converted. And if you were to take any type of radioactive particle and you plotted how much of it was present at different times, and in this particular graph we're looking on the y-axis of percent, so we're going to start at 100%, and we're going to look at it over time. Now you'll notice the time units here are not in minutes, seconds, years, centuries, or whatever, they're in half-lives. So this graph will be true of every radioactive species. You'll just put a different value in for each half-life. So one half-life would be the time it takes for half of it to go away. 2 half-lives would be a half of whatever's remaining would go away. So the curve would look like this. So you see after 1 half-life, whatever that period of time is, and it might be very short, a fraction of a second, or it might be billions of years. After 1 half-life, and every isotope, every radioisotope, has its own specific half-life. They're all different. And so after 1 half-life, any one of those, whatever its half-life is, it will be down to 50% of the original. After 2 half-lives, it'll be down to 25% of the original, or 1/4. After 3 half-lives, you cut it in half again, 12.5%, or 1/8. After 4 half-lives, 6.25%, or 1/16. And after 5 half-lives, 3.125% of the original, which is 1/32. And you can keep doing this, cutting it in half for as long as you want, for as many half-lives as you want. Typically, we say that the radioactivity is essentially gone after about 10 half-lives. That usually gets rid of the bulk of it. Typically, it gets rid of about 99.9% of any radioactivity, but it's going to be a different amount of time depending on what the half-life is. Now, so with each half-life, 50% will go. So you'll notice at 1 half-life, we're at 50%. So at a second half-life, we're half of the 50%, et cetera, et cetera. So if you're interested in the math, and you're not responsible for this in any introductory course, but the half-life is directly related to the rate constant, because the half-life is equal to the natural log of 2. This is not the log log of 2. This is the natural log, ln on your calculator, log of 2, which is about 0.693, divided by the rate constant. In other words, the rate constant goes up, the half-life will go down. The rate constant goes down, the half-life will go up. And here's it in a little bit more explicit with the math. And you could flip this. If you know the half-life, you can always calculate the rate constant because it's log 2 divided by the rate constant. But you're not responsible for this advanced material. So here are a list of radionuclides. I'll show some very commonly used ones and then some not so common ones. I've shown right here hydrogen-3, also known as tritium. Hydrogen's isotopes, hydrogen 1, 2, and 3, the naturally occurring versions of hydrogen's isotopes, each have names. It's the only element on the periodic table for which there are names, individual word names for the isotopes. So Hydrogen 1 is called protium. That's not used very often. Hydrogen 2 is called deuterium, so it might be symbolized with a D. And hydrogen 3 is tritium with a T. And tritium is the radioactive one of those three. The other two are actually stable isotopes of hydrogen. And hydrogen 3 has a half-life of about 12 years, so after 12 years, half of it's gone. After 24 years, another half is gone, so you're only left with a quarter of the original. You've lost 3/4, etc. Carbon-14, which is used for dating artifacts from anthropology studies, has a half-life of 5,730 years. And both of these isotopes are beta emitters. Iodine-131, also commonly used in the labs, or at least it used to be, all of these are being phased out of labs, is both a beta and a gamma emitter, so it's quite dangerous to work with. You have to use lead shielding to protect yourself from the gamma rays, and it has a half-life of only 8 days. And sometimes this is actually attached to certain organic molecules and injected into people for imaging studies, but since it only has a half-life of 8 days, after about 80 days, 10 half-lives, it's pretty much gone in the person. Some other isotopes, iodine-125, fluorine-18, which is used in PET scans, sodium-24, iron-59. These are either beta emitters, that's the B with a minus sign, or the antiparticle of beta, positron emitters, that's the beta with the plus sign. You're not responsible for positron, I'm just pointing it out. And they all release gamma at the same time. So they all are you have to use some safety precautions to work with any of these. And you'll see they have a variety of different half-lives. And the Y stands for years, the D is for days, and you see the range is quite wide. Here's some more, cobalt-60, which used to be used a lot. It's now used in certain cancer treatments. That has a half-life of a little over 5 years. Nickel-63 and americium-241 are actually used in smoke detectors. And you can see they have half-lives in the hundreds of years, meaning if you keep your batteries replaced, your smoke detectors should last for quite a while. Uranium-235, which was used in the first atomic bomb, has a half-life of 7 times 10 to the 8 years. That's 700 million years. And half-lives can be incredibly long or incredibly short. Here are the two of the very longest half-lives known, bismuth-209 and tellurium-128, whose half-life was just calculated this year. So that was a pretty big deal. And these things have half-lives that are longer, much, much longer than the age of the universe. The age of the universe is 13.8 billion years, 1.38 times 10 to the 10 years. And you look at the values for the half-life of bismuth-209, that's 1 billion times the age of the universe. And it's even more for tellurium. That's more than 1 trillion times the age of the universe. So these things, while they're technically radioactive, are actually incredibly stable. You can hold them, you can hold bismuth-209 in your hand, it's not going to hurt you because its decay is so incredibly slow. And then you have on the opposite end of the spectrum, hydrogen-7. This is a man-made isotope, as are many of the ones shown in here, that is so crazy unstable, it has far too many neutrons in it. So hydrogen-7 would be 1 proton and 7 neutrons. It spits out neutrons as fast as it can. So within 10 to the 20 to the minus 23 of a second, which is an incredibly short period of time, it immediately releases 4 neutrons to become hydrogen-3 up at the top of this chart, which can then have a half-life of 12 years. So that's a giant difference from one isotope of hydrogen to the next. So when we talk about half-lives, there are a lot of calculations that can be done. We're going to keep it relatively simple for this course. They're going to be in whole numbers of half-lives. It takes more math to do on any length of time, but if you're using round number versions of half-lives, like 1 half-life, 2 half-lives, 3 half-lives, the math is actually incredibly easy as long as you keep track of what you're doing. So here's the problem. The half-life, the T1 half for nickel 63 is about 100 years. It's actually 101.2 years, but let's keep the math simple here. 100 years. So if you had 100 grams of this isotope, how much would remain after 200 years? Well, you know that if you're starting with 100 grams at 0 years, that's 0 half-lives. After 1 half-life, 100 years, it's going to go down to half of that, 50 grams. And if you wait 200 years, it's going to go to half of that, 25 grams. And you could keep doing this. 300 years is a third half-life, 12.5 grams. 4 years, 400 years is 4 half-lives, 6.25 grams. 5 half-lives, 500 years, 3.125 grams. 600 years, 6 half-lives, 1.5625 grams. And you can just take your calculator, type in the original amount, divide by 2, and just keep dividing by 2 for as many half-lives as you need to count, and that will tell you how much you have left when you're done. So in this case, you can see that it takes a long time for all of the nickel 63 to disappear, hundreds and hundreds of years. And like I said before, this is used in smoke detectors. It's one of a couple different isotopes that's used in smoke detectors. Here are a couple problems that are more typical of what you'll see on an exam. The half-life, T1/2, for nickel 63, and now I'm using the real value, and I'm showing you the complete symbol for nickel 63, 63 at the top. That's the mass number for this isotope of nickel, and all nickel has an atomic number of 28. Is 101.2 years for the half-life. How much of the 200.0 becquerel sample would remain after 306.6 years? Well, becquerel is one of many units that you use for radioactivity. We have disintegrations per second, disintegrations per minute. Disintegrations per second are becquerels. We also have curies and millicuries and microcuries. It's not important what unit it is, because you're going to keep with the same unit from the beginning of the calculation to the end. So just make sure you use the same unit within a question. Well, you've got 306.6 years. The first thing you need to do is figure out how many half-lives this is. Well, the number of half-lives is just how much time, which is 306.6 years, divided by 1 half-life, which in this case is 101.2 years. So it's just 3 half-lives. And I'm not going to worry about significant figures here because the calculations are a bit more complex for determining sig figs. I'll tell you how many I want. In this case, I'm asking for 4 sig figs. So if you know it's 3 half-lives, just take your starting material and cut it in half 3 times. After 1 half-life, you go to 100.0 becquerel. After 2 half-lives, 50.00 becquerels. Third half-life, 25.00, and I kept it as 4 significant figures all the way through so that my answer is in the right number of sig figs at the end, 25.00 becquerel. In other words, 1/8 of the original, because 3 half-lives means a half, a quarter, an eighth of the original. 3 times I'm cutting it in half. The next question, the amount of radon-224, and I've shown the full symbol here, this isotope decreases from 2.320 microcuries to 0.145 microcuries in 428 minutes. What is the half-life of the isotope? Now, you might be looking at this and say, I don't know how to even approach this. Well, what you should notice is that you're given the starting radioactivity and the final radioactivity and the total amount of time. So if you know the starting amount of radioactivity and you know the final, you can plug in the starting amount of radioactivity into your calculator. And this is what you're going to do. You're going to put in radioactivity into your calculator and divide it by 2 until you get 0.145 microcuries. And that will tell you how many times you had to divide it by 2. So if I do that, you see if I plug in 2.320 microcuries into my calculator, I cut it in half. That's not enough, 1.160. I cut it in half again, 0.580, still not enough. Cut it in half a third time, 0.290. I'm getting close, but not there. Divide it one more time, and voila, I have 0.145 microcuries after I've cut it in half 4 times. I've halved it 4 times, 4 half-lives. Well, if 4 half-lives is 428 minutes, I just take the time, 428 minutes, well, I know that the number of half-lives is the time divided by the number of half-lives, I'm sorry, by the time of the half-life, and I can rearrange that. So a half-life, one half-life, is my total time divided by how many half-lives I have. And don't look at the formula. Think of it just logically. If I know 428 minutes is 4 half-lives, well, then I divide it by 4 to get 1 half-life, which is 107 minutes. So the answer to this is that it has a half-life of 107 minutes. Here are 2 more problems. The half-life of carbon-14, C14, is 5,730 years. An archaeological sample of wood was found to contain only 3.125% of the original radioactivity observed in living wood. How old is the archaeological sample? Well, what's implied in this question is that living wood is always replacing the carbon in it. So you're not going to see changes in the radioactivity until the wood is dead, until somebody chops the tree, cuts the wood up, and makes something from it. And the second that happens, the tree is no longer putting in new carbon-14 into the wood, and therefore you can watch the carbon-14 go away with time. And you're told that after a certain amount of time, an unknown amount of time, you're down to 3.125%. Well, what did you start with? Well, what you started with must have been 100%. So if you start with 100%, you type, that's how much radioactivity you have. It could be percent, it could be microcuries, it could be disintegrations per minute, it could be becquerels, whatever the unit is, that's what you plug in your calculator, and you cut it in half until you get to what you need to get to. Well, in this case, we're trying to get to 3.125%. So if I start with 100%, I divide it by 2, I get to 50. I divide it by 2 again, I get to 25. After 3 half-lives, 3 cutting in halves, 12.5%. After 4, 6.25. After 5, 3.125%. I'm at the amount that I need to get to. So I've had to cut it in half 5 times, which means I must have had 5 half-lives. Well, if I know there are 5 half-lives, and I'm told right in the problem what 1 half-life is, 5,730 years, well, 5 times that is 28,650 years. Now, the question asks for 3 sig figs, so I round it to 28,700 years. So my archaeological sample must have been 28,700 years old because it underwent 5 half-lives of the carbon-14. And the last example here, a sample of contaminated water contains 32 microcuries. Remember, we're not worried about what the unit is. We're worried about it changing. We start with 32 microcuries of radioactivity due to the presence of cesium-137 due to a nuclear accident in 1986. And I'll just pause here and tell you, in 1986, there was a major nuclear accident at the Chernobyl nuclear power plant in what is now the Ukraine. And this was an enormous accident. A lot of people died in this accident, especially trying to stop the fires inside the nuclear power plant, which would have resulted in an even greater release of radioactivity to the general population. So these people were heroes. But in 1986, this happened. And we're going to assume that you have a sample of water with 32 microcuries in it in 1986. The half-life of cesium-37 is about 30 years. So the question is, in what year will the radioactivity of the sample be down to only 0.50 microcuries? Well, you're given the starting radioactivity, you're given the final radioactivity, and you're told what a half-life is. Well, first you have to figure out how many half-lives happened. Well, if you're starting with 32, you cut it in half until you get to 0.50 microcuries. So you plug 32 in a calculator, divide it by 2, you get to 16, not enough. Divide it by 2 again, 8. Divide it by 2 again, 4. Divide it by 2 again, 2. Down to 1, down to 0.5 microcuries. And if you count how many times you divided it, you see that you cut it in half 6 times. So you must have had 6 half-lives in this question. Well, 6 half-lives, remember every isotope has a different half-life. This isotope has a half-life of 30 years. 6 half-lives is 6 times 30 years, or 180 years. But the question says, in what year will the sample be down to this lower level? Well, if you started in 1986 and you have to wait 180 years, that means this sample won't be down to 0.50 microcuries until the year 2166. So these kinds of accidents are incredibly serious. It takes an enormous amount of time for the area to be safe. And in fact, that plant was so dangerous, it was covered with a giant shell of solid concrete. And after about 30 years under this concrete, the radioactivity inside was so strong that it started destroying the concrete, and they had to put a new dome over top of it just in the last couple of years. So it's a major deal when you have a giant nuclear accident like this, and it's why you have to be so careful working with radioactivity. And we'll stop here.